Hello everyone. In this video, I will be discussing data handling in analytical chemistry. This is the first part of a lecture series on analytical chemistry. Let us start with the term accuracy. Accuracy refers to how close a measured value is to the true or accepted value. Basically, it indicates the correctness of a measurement. If an instrument or a particular method provides measurements that are close to actual value, it is considered accurate. Let us understand with a suitable example. Suppose a thermometer measured the boiling point of water as 100.2 degrees Celsius when the actual boiling point is 100.0 degrees Celsius. This measurement is accurate because it is very close to the true value. Coming to the related term precision. A precision refers to how close multiple measurements are each other regardless of whether they are close to the true value. Basically, it indicates the reproducibility or consistency of measurement. If repeated measurements give nearly the same result, the instrument or method is considered precise. Let us understand with a suitable example. If a balance gives the following repeated weighting value for the sample like 2.503 gram, 2.504 gram, 2.502 gram, 2.503 gram. The values are very close to each other, meaning the measurement is precise, even the true value is 2.600 gram. This concept can be illustrated using target practice. All the bullets are landed in the bullseye, so you are both precise as well as accurate. In the second one, all the bullets are clustered together but not in the bullseye. You are precise but inaccurate. This indicates that the gun is slightly misaligned. In case of third one, all the bullets are scattered. You are imprecise and likely inaccurate. And the next term is significant figures. Each measurement contains some uncertainty due to the limitation of instrument and human error. The significant are the digits in a measurement that are known with certainty plus one estimated one. For example, measuring the mass of apple using a manual scale give 1.5 kilogram, but an analytical balance give 1.512 kilogram. The last digit in a measurement is always uncertain. Significant figure helps express the precision of a measurement properly. If we record a volume as 11.2 ml, the digit 11 are certain, but the last digit 2 is uncertain. The uncertainty in the last digit is always assumed to be plus minus 1. This means the actual volume could be anywhere between 11.1 ml to 11.3 ml. Unless otherwise stated, uncertainty is always assumed to be plus minus 1 in the last digit. For example, in the number 237, we have 200, 3 tens and 7 units. If this number is reported as a final answer, it implies that uncertainty lies in the unit digit. That means the number may be lie in between 236 to 238. Let us identify significant figure using some significant rule. The first one is non-zero digits are always significant. For example, in case of 123.45, there are 5 significant figures and the digits are 1, 2, 3, 4 and 5. In case of 12.34, there are 4 significant figures and that significant digits are 1, 2, 3 and 4. Rule number 2. Zeros between non-zero digits are significant. Example, 102.3, there are 4 significant figures and you have to count 0 as well as a significant digit. In the number 102.03, there are 5 significant figures and both of the 0 digit will be counted as significant figures or digit. Number 3, leading 0, I mean before non-zero digit are not significant. For example, in case of 0.045, there are 2 zeros just before the non-zero digit 4 and 5, but they are not significant, so we won't count it. So in case of 0.045, there are 2 significant figures and the significant digit are 4 and 5. Similarly, in case of 0.0305, although there are 5 digits, but the number of significant figures are only 3 and the significant figure digit are 3, 0 and 5. Rule number 4, trailing 0 in a decimal number are significant. Like in this case 23.00, these 2 0 are coming after the non-zero digit number, so it will be countable. So there are 4 significant figures in case of 23.00. Similarly, in case of 18.000, there are 5 significant figures. Here in this case, all the 3 0 will be countable. Number 5, trailing 0 in a whole number without a decimal are not significant. Consider the example 5,000, 500. There is no decimal place and all the 3 0 will not be countable. So there is only one significant figure and the significant digit is 5. But if you are writing like this 500 point, that means you are placing a decimal place after the 3 0, then you have to count all the 3 0 as a significant figure. So in this case there are 4 significant figures. Now measuring with significant figure. Now let us apply this concept when the reading measurement. Suppose we are using a burette to measure a liquid. If the liquid level falls between 30.2 ml and 30.3 ml, we estimate the last digit and record it as 30.24 ml. Here the first digit 30.2 are certain and the last digit 4 is uncertain. This estimated digit improves precision and follow the significant figure convention. Placement of decimal point in significant figure. The number of significant figure does not depend on where the decimal point is placed. Example 92,067. Whether we can write it as 92,067 micrometer or maybe 9.2067 centimeter or maybe 0.92067 decimeter or maybe 0.092067 meter. In all the cases we have 5 significant figure. The value may be expressed in different units, but the precision remains the same. Scientific notation and avoiding ambiguity. Sometimes number can be misleading if we don't express them correctly. For example, 9,36,600. How many significant figures does it have? It is still unclear. To remove this ambiguity, we use scientific notation. If we write it as 9.3660 into 10 raised to the power 5, it has 5 significant figures. However, if we write 9.366 into 10 raised to the power 5, it will have 4 significant figures. This method ensures clarity in reporting value. Rules for significant figure in calculation. Addition and subtraction. The answer should have same decimal places as the least precise measurement. For example, 12.34 centimeter plus 0.056 centimeter is equal to 12.396 centimeter. As the least precisely known number is 0.056, which is reported up to 3 decimal place. In case of multiplication and division, the answer should have same number of significant figure as the least precise value. For example, 4.56 into 1.4 is equal to 6.384, and this is rounded to 6.4, as the least precisely known number is 1.4, which has only two significant figures. In case of log and antilog, let us talk about first logarithm. In a logarithm of a number, keep as many digits to the right of the decimal point as there are significant figure in the original number. Let us illustrate with suitable example, like in case of log 4.000 into 10 raised to the power minus 5 is equal to minus 43979. As in case of 4.000 there are 4 significant figure, so the answer is reported up to 4 decimal places. In case of antilog, keep as many digits as there are digits to the right of the decimal point in the original number. For example, in case of antilog of 12.5, the answer will be 3 into 10 raised to the power 12. As in 12.5 there are only one decimal place, so the answer is reported only with the one digit, that is with only one significant figure. Coming to the rounding off in measurement. Rounding is done based on the digit that follow the last significant figure. If the digit is greater than 5, round up to the next higher level. If the digit is less than 5, keep the last significant figure unchanged. For example, 9.47 rounded off to the 9.5, as 7 is greater than 5, so we can round it up. Now in case of 9.43, it is rounded up to 9.4, as 3 is less than 5, so the number remain the same, 4 remain the same. Some special cases like rounding off when the last digit is already 5. If the last digit is exactly 5, use the even number rule. Round it to the nearest even number to minimum base. Example, 8.65, 6 is even, so we can round down, so number will be 8.6. In case of 8.75, 8 is even, so we can round it up to 8. 8.55, so 6 is even, so we round it up. Coming to the next topics, as there are two main classes of error that can affect the accuracy or precision of a measured quantity. So let us first talk about the determinate error. Determinate error or systematic error are determinable and can be avoided or corrected. They are constant error, such as uncalibrated pipette used for all volume deliveries. Example, a 10 ml pipette accurately deliver 9.95 ml, causing a constant error of 0.05 ml. A determinate error can be a variable error, such as burette with a volume reading that vary at different level. The error can be proportional to sample size. Example, a 1 ml burette reading is actually 0.99 ml, causing an error of 0.01 ml per ml. So the total error increased with the volume of the titrant used during the course of titration. There are three types of systematic error. First one is instrumental error. All measuring devices are potential source of systematic error. For example, pipette, burette and volumetric flasks may hold or deliver volume slightly different from those indicated by their graduation. These differences arises from using glassware at a temperature that differs significantly from its calibration temperature. Method error. The unusual chemical or physical behavior of the reagent and reaction on which an analysis is based often introduce systematic method errors. The slowness or incompleteness of the reaction, instability of some species and side reaction can interfere with the measurement process. For example, an excess of a small indicator in volumetric analysis can significantly shift the endpoint from the equivalence point. The third one is personal error. Many measurements require personal judgment. Example include estimate the level of liquid with respect to graduation in a burette. One person may read the upper meniscus, another may read the lower meniscus, and the third may read the middle meniscus, resulting in the different recorded value, like it may be 19.8, it may be 20.0, or it may be 19.9. The next type of error is indeterminate error. They are random. The indeterminate error, often called accidental or random error, which represent the experimental uncertainty that occurs in any measurement. These errors are revealed by small differences in successive measurement made by same analyst under the virtual identical condition, and they cannot be predicted or estimated. The indeterminate error should follow a normal or maybe a Gaussian distribution. Such a curve is shown in this figure. It is apparent that there should be very few large errors, or that have should be very equal number of positive and negative errors. Example, an automatic packaging machine for dates weigh 500 to plus minus 10 gram because the mass of date is not fixed due to variation in size and moisture content, etc. Now I end this video here. Make sure to like and subscribe if you find the content helpful. Stay tuned for the next video on analytical chemistry. Thanks for watching.